All right, today we're going to look at two equations that are going to connect some things. The first one is the connection between free energy and voltage. A lot of times they're going to ask you to tell them what the free energy of a reaction is, and all you'll have is a reduction potential table and a redox reaction. So this is a redox equation, and you have your reduction potential table chart. And if you're asked to solve for free energy, you would utilize delta G is equal to negative N S E. It's delta G naught, negative N S E naught. This is on your AP equation sheet, so you don't have to memorize it. Let's look at what everything is. We know delta G is energy, free energy, and what are the typical units of that? Joules. Okay. N is the number of moles. We know N is moles, but specifically it's moles of electrons. What it is the moles of electrons that you canceled out, that common factor. So if you had 2 in one equation and 5 in the other, what would your common factor be? 10, and you would write 10 moles in there. So this is moles of E. A Faraday, I don't like the units they use here. They make it harder, not to mention that the units on the AP equation sheet match what I say. But what a Faraday is the number of joules, I'm sorry, not number of joules, it's the amount of charge that a mole of electron carries. In physics, you probably learned what the charge on one electron is. Does anyone know that number? 1.6 E negative 19. If you take that number, since that's one electron, multiply it times 6.02 times 10 to the 23rd, that's the number you're going to get. Okay? So this is actually the number of coulombs per mole of electrons. So the units on this guy are coulombs per mole. And then E we know is in volts, but I want you to know what a volt actually is. And what is a volt? A joule per coulomb. So looking at that, you see that all the units work out. Okay, if you're solving for joules, coulombs cancel, moles of electrons cancel, leaving you with joules. And the sign also works. If we have a positive E, we know it's spontaneous. That would give us a negative delta G, which is also spontaneous. So just pay attention to that. So let's go ahead and use it. It's a simple, I'm only doing one problem to show you how to do it. It's not hard. Calculate the standard free energy and, oh, I didn't see that last period, and the equilibrium constant. So we'll talk about that in a minute, but let's find that free energy first. How do I find that? What do I need to calculate to use that free energy equation? E naught. Where do I get E naught from? Redox. So what do I do first? I'm going to write out my half reactions. I don't have to figure out really because it's done for you. Okay, start looking these up, folks. Reduction PB is as it is going to be on the table, so find it and tell me what that is. It's PB 2 to 0, and then we need the reverse of the magnesium because it's oxidized. So we're going to make it positive 2.356. 0.125. So our E naught is going to be equal to the sum of that. So we get, looks to me, we get 2.231 volts. Is that what y'all got? All right. So that's our volts. So now we can take those volts, also known as joules per coulomb, and plug it into our equation. I'm really insistent that you guys plug your units into the equation. There are a lot of you, again, on that last test that did exactly what I said you were going to do. You used ghetto homies. You got overwhelmed because you were worried about time and all this stuff, and you had kilojoules and joules in the same equation, and you missed the problem. If you would have written down your units, you would have caught that. Write the units as you plug stuff into your equation. So negative N, what was the number of moles of electrons if we were to cancel them out here? How many is that? 2. So that's 2 moles of electrons. Negative N, S, is 96,500. That is the charge per mole of electrons. So moles of electrons are going to cancel. And then negative NS E naught, 2.231 joules per coulomb. Coulombs cancel, and you see I have a final unit of joules. So what is my delta G? Let's not use the constant. The moles is an exact number. Let's just do 4 sig figs based on our E. Let's get the right number. Negative 430,600 joules. Does anyone else agree with that? All right. So that's our joules. That answers the first part of the question. Now the next part, which is a common thing they do, they're like, okay, well, what's the equilibrium constant? How do we connect all of this to equilibrium constants? Negative rattling. Delta G is equal to negative RT/ln of K. Let's predict. If it's spontaneous, K should be greater than or less than 1. Spontaneous in the forward direction. Greater than 1, and that's what we're going to hope for. So we're going to put negative 430. I need to be in joules here because of the R. Negative, what was my R again? 8.31 joules per mole K. My temperature, since this G is technically standard from that original equation, what would my temperature be? 298. And then ln of K is what we solve for. So go ahead, just break it down into steps. Go ahead and solve for ln of K. Go ahead and just divide by negative 8.31 and 298 and tell me what you get. Times 10 to the what? That's dividing that and that and that? All right. You must have solved for K. Yeah, I wanted this. So now we're going to go e to the both sides of this. And what do we get? That's huge. Is that what y'all got? Okay, so that's definitely not greater than 1. It's definitely spontaneous in the forward direction. All right, any questions on how to use negative NFE and relate it to ratlink? All right, the next and final equation that I'm going to have you get to know is something called the Nernst equation. The Nernst equation is not on the AP sheet. In fact, they have actually taken off the mathematical use of this on the AP and want you to do a verbal explanation of what happens when you change conditions of a cell. I, however, want you to use it because it's going to be used in a lot of the universities where I'm teaching at this point a little bit above the AP. However, as kind of a compromise, I will give you the equation. You're not going to have to memorize it. And before the AP, we'll put it on your calculator because they don't clear your calculators. And there's no, it's not illegal. If they were concerned about it, they would clear the calculator. So we're going to do it mathematically the way I've always taught it and the way they actually tested on it until this year. And I'm also going to explain the verbal explanation as well. They're not going to not accept that equation. They just don't expect you to use that as an explanation. So we're going to do these problems two ways. Basically what the Nernst equation is instead of the E naught, it's calculating a new E when conditions have changed. This first version is when you're at non-standard temperatures or non-standard concentration of 1 molar. That one has never shown up on the AP. What they always do is just mess with those 1 molar concentrations, and this is the version that I'd expect you to be able to use. Okay? I'll rewrite it and let's talk about it. E cell is your non-standard E is equal to the E naught. So you have to find the standard E the same way you already know how. Minus 0.059 over N log of Q. So N again is your number of electrons that you canceled out in the balanced equation, the moles of electrons. Now the log of Q, let's talk about this for a second. Q is really basically K, but it's K when we're what? What's the difference? Not at equilibrium. Why is a battery really not at equilibrium? What does it mean to be at equilibrium? You have a forward and a reverse reaction of the same rate. Is that how batteries work? What do batteries do? We go one direction. We call it a driving force in one direction, and that's where the difference in potential is. If there's not a difference in potential, you're not going to have that driving force to move the electrons. If we're at equilibrium, we have a dead battery. So that's why it's just Q there instead of K, but we're going to treat it exactly the same way we've done other Qs, where Q is equal to concentrations of the products divided by the concentrations of the reactants raised to the coefficients in the balanced equation. That's it. And it's really, really easy because most of our stuff in our balanced equations are solids because they're solid electrodes. Do we put solids in the equilibrium expressions? No. So this is really a pretty easy thing to do. So we're going to get there, but the first thing just is to calculate E naught. So how do we calculate E naught? A little review. Redox, that doesn't help me. Okay, but I'm going to look at the table. I still have to do something before I do that. Write my half reactions. So zinc going to zinc plus 2 electrons. And my other half reaction is copper plus 2 electrons goes to copper. Because I know what's coming, I know I'm going to need to use the Nernst equation. I need that balanced equation overall. So I'm going to cancel these out, and I get Cu plus 2 plus zinc makes zinc plus 2 plus Cu. All right, so let's get our voltages because we need that numerical value. I know this is 0.34 volts. The zinc is going to be opposite because you look on the table, it's not reduction, it's oxidation. So someone find it and tell me what it is. All right, it was negative. We're going to make it positive because it is reversed. Someone in first period asked me, well, how do you know that you have to flip it? How do you know? Looking at that, do you see how that is reversed to what's on the table? The table's telling you whether to leave it alone or flip it. So you got to look at the table. And then our voltage ends up being 1.002? Oh, 1.102, that's right. We got to carry the 1.102 volts. Okay, so that is our E naught at standard conditions. So looking at this next problem, it says, calculate the E cell when the ratio of these concentrations is small. That is, if Zn plus 2 is 1 times 10 to the negative fourth and the copper is 1. What were the concentrations when E naught was in existence? Everything was 1 molar. So really, we just changed the concentration of the zinc. So mathematically, what you would do would be doing the following. Just plug into the Nernst equation. E cell is equal to E naught minus 0.059. What was our common factor of electrons that we canceled out? 2. Now log product concentrations over reactant concentrations. We only have the concentration of the zinc plus 2. Why not the copper? That's solid, so we don't put it in there. So the zinc is 1 times 10 to the negative, is that a 4? Because I wrote over it. Negative 4 raised to what power? 1, divided by the copper concentration of 1 raised to the 1. Now, before you do anything, you could do this without a calculator. You can't necessarily get the exact number, but I want to predict, based on log rules, what is going to happen here. Let's talk about our log. If we have a log of a number greater than 1, that's going to be positive. And you just need to know this. It's good to know. A log of a number less than 1 is going to be negative. Is this number greater than or less than 1? Less than 1. So this whole thing is going to be negative. A negative times this negative means we're going to have a positive increase in voltage. So we're going to predict an increase in voltage. So go ahead and put it in your calculators. It's not a drastic difference. Can you give me 3 decimals, I mean. 220. Can I get a second on that? I don't want to put it wrong on the video. We had a really bad day in thermo where literally everything on there was wrong. There's too many calculators in here to make mistakes. All right, 1.220. Okay, so that's our voltage. Now, if you were to ask to predict whether the thing would increase or not increase, and you don't have the Nernst equation, again, I'm going to give it to you on the test. It's going to be on the board, and we'll put it into your calculators before the AP. if you were to do it in terms of theory, this is what they want you to do. Let me rewrite the equation. And I'm really not comfortable with it because they try to make this seem like Le Chatelier's principle, but that's then assuming things are at equilibrium, and batteries are not at equilibrium because they'd be dead. So I'm not 100% comfortable with this, but when you're in a pinch, say you forget, your calculator dies and you don't know the Nernst equation, okay? What you would do is look at this reaction, and remember, when E was at E naught, this and this were what concentrations? 1, right? So what did we do? We took away zinc and decreased its concentration. By decreasing its concentration, we're increasing, if you think about Le Chatelier's principle, the forward driving force of the reaction to replace that zinc. So if we're increasing the forward driving force, what are we doing to the voltage? Increasing the voltage. So removing zinc or decreasing the zinc plus 2 concentration leads to an increase in the driving force of the reaction. Therefore, voltage increases. Got it? So if you're asked to predict, I will accept this as a prediction, or I will accept using the Nernst and saying, hey, log of a number that's positive is greater than 1, log of the number that's negative is less than 1, whichever. I'll accept either. Got it? Questions? All right, let's do one more problem. We ready to move on? Calculate E cell, okay, which is made of those components. Something should be jumping out at you to make you realize this is a Nernst equation problem, that we have a non-standard cell. Different molarities, exactly. I know it says cell, and people are like, oh, it says cell, but it might not say cell. It might just say E. It's the fact that we're not at 1 molar. So this is going to encompass a lot of little issues that we have to tackle. Again, we need a spontaneous cell because it's a voltaic cell that we're dealing with, so we want a positive voltage. What did they not tell us here, though? Exactly. What's being reduced and oxidized? So this should be a +1, by the way. So what we're going to do is write both of these as reduction half reactions first, like we did in that other voltaic cell problem we did yesterday. And look those reduction potentials up and figure some stuff out. I think silver was 0.7 something. 0.799 volts. And the cadmium as is was 402? Negative 0.402 volts. So there are my voltages. Now, which one should I flip? Which one's less reduced? The cadmium. So I'm going to flip everything including the sign. I'm going to get positive 0.402. And I'm going to get, hold on, what? 1.201 volts. CD goes to CD plus 2 electrons. Because I know I'm going to have to use the Nernst, I want to get a balanced overall equation. So I'm going to have to multiply the top one by 2. Do I multiply the voltage by 2? Nope. My push per Peter does not change. Gives us 2 silver plus CD plus 2. So this is my balanced equation. I have to have that because when I get into that ratio for Q, I need those stoichiometric coefficients. Okay, so now I can plug and solve into the E cell. E is equal to my E naught of 1.201 volts minus 0.059. What is my common factor of electrons? 2. It's not always 2. I know everyone we've done today has been 2, but it's not always 2. Times the log products. Look at the products. Which product do we have a concentration of? Cadmium ion. And what is it? 1.5, and I raise it to the 1 because there's a 1 here. Divided by which reactant do I have a concentration of? silver, and it's 0.2, and what do I do to that? I square it. So before we even do it, let's do a prediction. We have a log of a number. This is obviously greater than 1. So that's what value? Positive. So we're subtracting off this whole number. So we should have a decreased voltage. When you do the math, what do you get? That sounds right. Pretty sure that's right. These aren't dramatic differences in voltages. Right? Is that good? Yes. No. The amount of concentration you would have to apply to change that would be pretty significant. It wouldn't happen. Let me ask you, if you were to look at a reduction potential table, how would you make the most high voltage battery? What would you mix? What would you do? Just the process. And you flip, exactly, you take the one with the highest reduction potential, leave it alone. The one with the lowest reduction potential, you'd flip it and then add them up, and that would give you your highest voltage batteries. So if you notice, a lot of times you hear we have 9-volt batteries, 9-volt batteries, and a lot of things you put together, you add them up, you're not getting 9. Where they're getting changes in voltage is through tweaking these concentrations. That's how we're getting the specific voltages that we see in different batteries. Okay. All right, let's do this explanation now with words. So remembering that this is the equation, this is our backup explanation. Originally, these two things were 1 molar, okay? But what did we do to the concentrations? We took away this, and we increased that. That's a double whammy. What did that do to the poor cell? Yeah, and I don't want to say shift left. My problem with that is we're not at equilibrium. So changing those things, that concentration isn't going to make the battery run backwards, okay? That's not what happens. Changing that does, though, taking away some of this, it's decreasing the driving force forward. And also, by increasing this, you're creating less of a driving force to make it. So you're double whammy decreasing the driving force of the reaction by decreasing concentration of Ag plus and increasing concentration of CD plus 2. Therefore, voltage does what? Voltage will drop or decrease. Voltage decreases. Okay? I don't care. Whichever you do is fine. I'm saying if you get a freak-out panic attack with the Nernst equation for some reason and don't have it to plug in and do the prediction, you can do it verbally. If they give you a direction and say you have to, in words only, do not use equations, I just don't know what they're going to do. Then you can do that. My problem with this is in the new curriculum, they refer to Le Chatelier and shifting, and the problem is, again, we're not at equilibrium. So you can't shift back and forth. There's only one way to make a battery run backwards, and that's, rechargeable batteries, right? So what happens in a rechargeable battery when you run out, you've either depleted your anode, or you've lost the ions on the other side, and you've run out of those. So by plugging it in the wall and forcing a current through it, you're reversing the reactions, rebuilding that anode, replenishing the ions in the cathode. And that's the only way you can do it. This battery is not going to naturally, you dump in some concentration of something, it's not going to reverse the flow. Okay, so to me that's an error in their logic, in their curriculum. And we've had discussions about it in trainings over the summer. But by the point where we got to really see it and talk about it, it was too late. They'd already printed it out and it had already been accepted and approved. So we're going to go with, I prefer to use the math, but if you do this, I'll take it as well. Just don't say it shifts backwards or something like that, because it doesn't. It doesn't. All right? Okay, I think that's it. Do y'all realize we have tomorrow's lecture, and then we have 2 organic lectures, and that's 3 more lectures for the entire year in AP Chemistry. That's it. We're almost done.